Okay, very good morning to everyone. I hope I'm audible and my screen is visible.
Yes, sir.
Thank you. So, yeah, so today's lecture must be noted down by group 4, ID number 19 to ID number 24. Do we have anyone in this group in the class? ID number 19, are you there? 20?
Yes, sir.
Okay. 21? Ruchi, your ID number? 19. Okay. Number 21, 22, 23, 24. Okay. So as of now, it's up to only the two of you. By the way, I have not received the notes from group 2 and 3, I believe. Right? Only group 1 has submitted, which is why you have slides and recordings of only the second lecture on the website. Group 2 must submit the notes today, okay? Otherwise, they lose their marks. Right? Today, I think it's like today is the 8th day, so submit it today. Anybody here from group 2? ID number, what would it be? 7, 8, 9? Anyone? 7, 8, 9, 10, 11, 12?
Excuse me, sir.
Yes?
Sir, I am ID number 11. We have submitted. Group 2 has submitted.
When?
Sir, we have submitted yesterday night.
Yesterday evening at least it wasn't submitted. Okay, I'll check and then upload the corresponding slides as well as the recording. We have about 98 students. Let's just wait for a couple of minutes and then begin with the class. Any problems with the tutorial? I hope you're trying them yourselves. And maybe now onwards, we'll try to upload the tutorial at least on Friday so that you have some time to try them out yourselves. Okay. Okay, while we wait for a couple of minutes, any comments, questions about the course? Are we going too slow, too fast? You can think of this course as a continuation to your discrete math course. So, I mean, if you have any suggestions, comments, you want me to change something, please let me know. The student thinks it is going as expected. You can think of this as a democracy. Please feel free to speak out, right? Any comments, anything? I mean, how is it going? I would like to know. See, if you were on campus, looking at your faces, I could have got some idea, but unfortunately, that's not possible. So please let me know. Otherwise, I'll just go through the motions and it becomes boring for me. That's the issue.
Sir, still mid-sem, it will be means syllabus of groups will be covered, and after that vector space will be covered, right?
So to be honest, this is the first time I'm teaching this course, so I don't really know. I would want to do that, right? I think ideally about 30 to 40% of the course should be groups and the remaining should be linear algebra. But we'll see. I mean, not made a plan in such great details so as to tell you that lecture number N will be covering groups and then N plus 1 onwards we'll do linear algebra. In the syllabus of this course, there is sort of greater emphasis on linear algebra simply because it finds its sort of applications more frequently. Right? Having said that, I'm not saying that groups are not used, but linear algebra is something that you will every now and then encounter in your other courses, starting this semester itself. Right? As I said, signals and systems is nothing but applied linear algebra. Is that okay?
Yes, sir.
Okay. Okay, let's begin. We have about 130 students. That's fine. Okay. So once again, group 4, ID number 19 to 24, you're supposed to take notes, prepare them in LaTeX and submit them no later than next Monday night. Okay. Right. Right. So this is where we were towards the end of the last lecture, and I think we proved this, right? Let H1 and H2 be subgroups of some group G, any arbitrary group G. The intersection of two subgroups is also a subgroup, right? So we answered this question affirmatively. Okay, so and then we asked this question. So PZ and QZ are two subgroups of Z. And of course, PZ intersection QZ will also be a subgroup, and it will be what subgroup? This would be equal to
LCM of
LCM.
P and Q,
LCM PNQZ.
Z.
Okay, I'm not sure whether we proved this, but I hope you can prove this, right?
Yes, sir.
So, yeah, if we have not done it, and if you have still not tried it, take it as a homework assignment. Okay, let's go ahead. So this is just written as a proposition here. Let's go ahead and look at something new. So let's take a group G, okay? And then let's just pick an arbitrary element A from this group, all right? We define, so this notation on the left-hand side, we'll see what it is called, but that is the notation, right? It contains the subset of G containing all powers of this element A. Okay, A to the power n for all n. Okay, so n of course is in Z, which means you include positive as well as negative powers of only one element A. So the natural question is, if we are looking at subgroups, put this subset with the same binary operation that is defined on G, right? Would that be a group, or would this subset form a subgroup of G as well? Anyone? So what two properties do we need to verify?
Closure and inverse.
Closure and
Closure
identity.
and inverse. Closure and inverse, right? Not closure and identity.
Yes, sir. Yes.
So how do we check closure? Once again, I mean, emphasize this earlier as well. Let me tell you once more. Some things may look very obvious to us, right? But it's equally important to be able to write it properly. Okay, so don't be lazy. So let's pick two elements, right? So how would two elements look like in this set? A raised to P and A raised to Q. P, two elements from this set. Okay, where P and Q are integers. What's the next step? How do we check closure? What would this be equal to?
Sir,
A
a to
raised
the
to
power
P
p
plus
into
Q.
the
Plus
power.
to be
P plus Q. Right? This, of course, is in this set because P plus Q is in Z. Again, you can see here we are using the property that Z with addition forms a group. Okay, so this is done. Inverse. A raised to P be an element in A for some P in Z. And then I think it is pretty straightforward to see. A raised to P into A raised to minus P. Same equal to 0 or this is the identity. Net again because 0 is in Z. Okay.
Sir, how can we say that a raised to 0 is always identity?
So I think I should have written it this way. Does it make sense now? So A raised to minus P into A raised to P is identity, isn't it? Yes or no?
Yes, sir. Can't we say it like that? We perform addition and subtraction on the powers. So with respect to addition and subtraction, zero is the identity. So a raised to zero
So
will be the identity.
exactly. So what you can do is you can just try this out, right? What would this be? For any P in Z, A raised to 0 into A raised to P, what would that be?
A raised to P.
A raised to P.
A raised to P, right? So A raised to 0 is the identity. If all right.
Sir, this in binary operations, addition and subtraction, this makes sense. But in other cases, this is this doesn't make sense. Like a raised to 0 equal to e. Means if we consider a polygon like triangle, and for that we consider the R1, R2, and FA, FB, FC. Then how can we say that
No,
FB?
no, no, no. See, what is this set? Right. So in your example, right, D3. Write this in a new
Yes,
page.
sir.
So you're talking about D3, right? I R120, R240, flip A. me try to be consistent with the notations. So is this equal to something like this?
No, sir.
No, right? So I'm not saying that this
So,
holds true for any group. Remember, we are assuming a very specific kind of a subset here. If you wish, you can take one element from this. So choose your favorite element from this set. Anyone that you wish.
R120.
R120. So what would be this equal to?
I R120, R240.
Now, so
Now,
what
sir,
would
means A is equal to R120. So A
right?
raised to 0 means, so A raised to 0 should be identity. So how
Yes.
can R120 be I?
See, what do you mean by A raised to 0?
Mul- it, Multiplication of element with its inverse.
Okay. So similarly, R120 composition, right? Multiplication here is the group operation is composition, isn't it?
Yes,
So
sir.
what is this equal to, right? This is R120 composed with R240, which is its inverse, right?
Yes, sir. Got
What
it.
is this? This is identity.
Identity.
Okay.
Okay, sir.
I hope I have convinced you and not confused you.
Yes, sir. Thank you.
Okay, so what we have basically shown is that this set is always a subgroup. Okay, and there is this specific subgroup is what is called a cyclic subgroup generated by this element A. Okay, once again, this particular set over here is a subgroup and it has a very specific structure to it. Right? It is called a cyclic subgroup generated by the element A. You may be wondering why cyclic, right? Any guesses? Any answers?
Sir,
Need
that
not be a guess.
table looks like cyclic. Table shows cyclic shift.
Table shows cyclic shift. Okay, it will be one answer.
Sir,
Anybody else?
after specific n,
Mhm.
we will get I, and the whole sequence will repeat itself.
Okay, so you are
Means
assuming something there, isn't it?
no, sir. Means I belongs to, means I is belonging to this set. So sir, after some k, a raised to k will be equal to I. So there is a whole cycle will repeat after that.
Okay. Can someone give me an example of a cyclic subgroup? A concrete example.
Z.
Sorry?
Integers.
Integers, right? Yes. What element generates Z?
1.
One. Right. So again, I am not good enough to recognize the name from the speech, but whosoever gave the previous answer, right? Somebody said the elements will start repeating after some integer. Right? Is that the case here?
Sir, if main group G is finite, then it is the
Yes.
case.
Right.
Otherwise,
So that's what I was looking for. So in the definition, right, it doesn't say anything about the size of the group. Okay, so the cyclic subgroup generated by an element A may be finite or may not be finite as well. Okay, so
Yes, sir. It was my mistake. Sorry, sir.
no, that's okay. I mean, right, not only you, I also make several mistakes, and I think it's good that you're making mistakes. Okay, so no need to be sorry. Okay, and several such examples are there. It's first, before we take up examples, let us look at some other definitions here. Okay, so if this element A, right, generates the entire group G itself, okay, which was the case with the element 1, right, generating the set of integers or Z. Okay, in that case, G, the group, is said to be a cyclic subgroup, or sorry, cyclic group generated by this element A. Okay, if an element A generates a proper subgroup, then we call that subgroup as a cyclic subgroup generated by A. If that element A generates the entire group itself, right, in that case, we say that the group G is a cyclic group. Okay. Also, if this element A generates the group G or it generates some proper subgroup H, okay, in both cases, this element A is said to be the generator of G or H. Okay, so the brackets correspond to each other. Right? Is that understood? Just a couple of new terms.
Yes, sir. Hello, sir.
Hello?
Sir, is cyclic, every cyclic subgroup is abelian?
Every cyclic subgroup is abelian. Can you prove that? It's not a very difficult proof.
No, sir, I'm asking you.
No, I mean, so now that you have asked, let's also prove it. So, what's your name?
Nishad, sir.
Nishad. Okay. So the statement is every cyclic group is abelian. Right?
Yes, sir.
Let us try to work it out. What do we need to show? For every AB in G, we need to show A dot B is equal to B dot A, or we need to at least check if this is true or not, right? We have as of now not said that every cyclic group is abelian or not, so we need to verify this. So how would we do this? Let's pick arbitrary elements from the group G. Okay, what do we know about the group G?
Cycle.
Cyclic. Since G is cyclic, how would two arbitrary elements of this group look like?
A to the power P and A to the power Q.
Right. P, two arbitrary elements. And I hope now you can sort of finish the proof, right? What is e to the power P into a to the power Q? E to the power P plus Q, which is equal to a to the power Q plus P. Why?
Associative.
No, this is not associativity. What is this?
Addition and substitution.
Exactly. Z is an abelian group. Okay, we are using that property. Once again, be careful, and then this is, I think now it's straightforward. Okay. Nishad?
Yes. Yes, sir, please.
Okay. Right. So this is another additional statement we can prove about cyclic group. Questions? Okay. Oh. One more additional term. Right. So let us pick an arbitrary element A from the group G. Right. The order of this element A is the smallest positive integer n. Okay, smallest positive integer n, such that A to the power n is A combined with itself n times. Using that particular binary operation gives you E. So we need to look for such an n such that A to the power n is E, and of course n has to be the smallest positive integer. Okay, and of course there's no guarantee that such an n exists. Okay, so in case no such integer exists, then we say that the order of A is infinite. Okay, so one straightforward example. What is the, I think I forgot to write the notation. The notation for order of A is either O of A, or sometimes we also write it like absolute value of A. Okay, but don't read this as absolute value of A, it means order of A. So what is order of 1 in Z?
Infinite.
Infinite.
Okay, let's look at some more examples so that understand what are cyclic groups. Okay, the other thing is also try to see that the order of this element A is the same as order of the subgroup that it generates. Here, I hope you recollect, we have already defined order of a group, right? Yes?
Yes.
Or no?
or no?
Yes, sir.
Yes. So,
So,
there's an echo from somewhere. Please mute yourself. So order of this element A has to be the same as order of the subgroup that it generates. Is that clear?
Yes, sir.
Everyone, I keep on hearing the same voices.
Yes, sir, it is clear.
Okay. Because this is going to be useful. Okay? If you do not agree with this, you can ask right now and try to prove this as a homework. So again, it looks straightforward maybe to some, but you must know how to prove this. Okay. Let's look at examples. So this one is straight from your signals and systems course. If you have not encountered it till now, you will encounter it sooner or later. 8 roots of unity. I hope you are familiar with this concept of roots of unity.
Yes, sir.
So, T is nothing but set of complex numbers such that z to the power n is 1. Okay, and don't get confused. This I stands for square root of -1. To know, maybe in your signals and systems course you use the notation J. Is that right?
Yes.
Yes. That is-
Right. So, okay. Now, is this a cyclic group?
Yes, sir.
Yes.
Yes, sir.
Okay. How are you so sure? So, if you have to prove that this group is cyclic, what do you have to show?
For element A raised to n, where n belongs to Z, are all in this group.
Once again.
For an element A,
Mhm.
all A raised to n, where n belongs to Z, are included inside the group.
Not only that, right? For some element A, there's a lot of activity I'll write down. Okay, you need to show this. So not only that this is included in G, but also this, right? Only then you can sort of conclude that this group G is a cyclic group. Right? And what do we call such elements A?
Generator.
Generator, right? So basically the idea is you need to find generators of G. If you are able to find at least one generator of the group G, then you basically proved that the group is a cyclic group. So what is the generator of this group? I mean, several of you were confident that this is a cyclic group, so then you should be able to give me a generator.
So all the elements in this generator.
No, sir, all I cannot generate.
So give me one generator.
So it is 1 by 1.
I'm unable to hear anything.
Sir, e raised to iota 2 pi by n.
Okay, let me try to. We are looking at 2 pi by 8th root of unity, right? So, and I hope you're familiar with this picture. would be e raised to I pi by 2 or I. This.
-1.
Okay, once you sort of draw this picture, I think you should be able to pick up the generator.
Sir, those which are not on axis.
Those which are not on axis. So would be this, 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 and this. Do all of you agree to this? So at least this should be clear, right? Why? Because I mean, what is e raised to I pi by 4? It's basically like rotation by 45 degrees, isn't it? So when you multiply e raised to I pi by 4 to any complex number, let's say x plus iy, what is the resultant? Anyone? It's like cos pi by 4 into x minus y sin pi by 4 plus I times y cos pi by 4 plus x sin pi by 4. Right. So if I look at this as the x coordinate and y coordinate, right, the real component corresponds to the x coordinate, the imaginary component corresponds to the y coordinate, and I sort of use the same interpretation here. This is nothing but x and y rotated by pi by 4. So if you apply I raised to I pi by 4 to any other complex number, let's say itself, this will basically rotate by 45 degree to give you I. You again apply e raised to I pi by 4 to I, you'll get this, then this, and back to this. Right? So you can easily see that it generates the group. Does it make sense? Okay, so the generators are, as somebody rightly pointed out, e raised to I pi by 4, but that's not the only generator. Okay, then maybe try and see. So with this interpretation, what is e raised to I 3 pi by 4? It's nothing but rotation by what angle?
135.
Okay, so let's say we want to check if this is a generator or not. So I'll apply e raised to I pi by 4 to 1. So I'll get e raised to I pi by 4. What happens if I apply e raised to I 3 pi by 4 to itself? Minus I. Okay, then
E raised to I pi by 4
then
minus 1.
this, then
Iota.
okay, I think we are done then. Okay, so you can see that you'd be able to generate the entire group even using this element. Similarly, I think you can try this yourself. You can generate the entire group using e raised to I 5 pi by 4 as well, and e raised to I 7 pi by 4 as well.
Sir, they are we can think of them as rotation by minus 135 degree and minus 45 degree.
Yes,
So
exactly. Yes. So it's the same thing, just change the directions. Okay? Or you can do it in anti-clockwise mode itself, right? You will be able to see that after certain iterations, you will get all the elements. Right. So this I think is clear. Okay, so these are the 4 generators. Again, I have not proved this, right? We are going to prove this, that these are the only 4 generators. Okay, but before we do that, let's look at other examples, because you possibly are wondering what is the importance of studying cyclic groups separately, right? The idea is they are frequently encountered in not only applications but in our day-to-day lives as well. Okay, so that's why we are looking at cyclic groups, and for now let's look at finite cyclic groups. So the second example is you have planar rotations. Okay, let's say you have a rotation by 30 degrees. So one element I'm specifying is rotation by 30 degree in a clockwise direction. Okay, and then all its iterations. So R30 applied to itself and furthermore. So what would the group contain? Course identity. Right. Of course, this I've defined it as a cyclic group. Okay, so there is no question about whether this is a cyclic group or not. What are the generators of this apart from R30? So because I've already defined G as being generated by R30, so this surely is a generator. Anything else that you think is also a generator?
So R60 is a generator.
Okay, how? So, for example, can you tell me how many iterations of, or how many times should I apply R60 in order to get, let's say, R30?
Uh,
Sir, R330 is a generator.
Okay, 330. Anything else? So the best way is just draw a picture, right? Whenever possible, of course. P 60, 90, 20, 50, 80, 10, 40, 270, 300, 310. So just assume this is not longer than the rest. Now, maybe this will help you figure out
generator. Sir, R150 and R210.
150, 210. Anything else? And anybody else? I mean, again, I'm hearing the same people participating. The rest should also participate. This is not a private tuition, right? Okay, so letters are R30, R150, R210, and R330. Okay, and again, at least in these two cases, you can draw this picture, and since the group operation is basically rotation in both the cases, you can sort of work it out, right? Just keep on performing the same rotations till you get all elements, and you'll see that you will hit all elements, okay, sooner or later.
Sir, we can find these generators using other method. Like
Yes,
this
yes, we are coming to that. Coming to that. Right now we are looking at examples. We have not yet given a theory to this, right? As of now, at least. And sort of in the next slide, basically, we are going to look at the sort of general structure of cyclic groups. Okay, but I just wanted, I mean, I could have given the statement directly, but I wanted to motivate it via several such examples. Okay. Okay. Next example, Z6 with addition modulo 6. How about this case? What is Z6? It is all integers 0, 1, 2, 3, 4, and 5, and together with addition modulo 6. Here it's very easy again. So what is the subgroup generated by 0?
It is 0.
0.
Input on 0.
Subgroup generated by 1? Sorry, anybody?
Z6 itself.
Itself. Z6. How about subgroup generated by 2?
0.
There is a lot of background noise. Please, somebody else can try. It's not a very difficult question per se, right? What is this?
024.
024.
024. Okay. Subgroup generated by 3?
03.
03.
4?
0.
024.
024. So
0.
the same as this, right? So again, remember, if you pick any element, it does not have to generate a new subgroup, right? It can generate a subgroup generated by some other element as well. Subgroup generated by 5. Again, somebody who has not answered, maybe if you can answer, that would be nice.
Z6.
Z6.
Good. So, what is the conclusion? What are the generators of Z6?
One and 5.
1 and 5.
Okay. So, you've seen several, not severally, in the sense of tens or hundreds, but at least what, 1, 2, 3 examples, right? And there's nothing special about Z6. You can, let's say, take Z8, Z10, Z9, whatever you want, right? Zn in general. We have the same pattern. Okay. So I want to figure out, so first of all, observe that all these 3 different groups, right? First of all, they are different groups in the sense that the elements that are part of the group are very different. Okay, one contains complex numbers, the other contains rotation transformation. So it is every element has a geometric interpretation to it. Third is just integers, right? With addition, modulo something. So by nature, these elements are very different, but at an abstract level. Right? Again, bringing the first lecture back, we are not interested in the behavior of the elements. What are the type of elements we are working with? But rather than that, we are interested more in studying the interrelationships between elements under the binary operations. In that sense, I hope you realize that all these three different examples have the same structure, right? Is that making sense? So
Yes, sir.
instead of
Yes,
this
sir.
R30, you could have seen Z12, right? With addition modulo 12. Would have been exactly the same. You could just rename R30 by 1 and you would have got Z12. Okay, Z12, why? Because this group contains 12 elements. 8th root of unity, you can see, has a very same behavior exactly like Z8. Okay, so even though the elements per se are very different, but the behavior of the elements with respect to the specific group operations that are defined on these groups, they are exactly the same.
Sir,
Yes,
sir, I just have one doubt.
go ahead.
Will the number of generators will always be an even number, or it's just in case of this?
Okay, hold on to your question. We are going to answer your question in the next slide.
Yes, sir.
Okay, so first of all, realize that we should not study all these examples separately if our motivation is to see what are the subgroups, right? Because again, subgroups is defined only using the binary operation among the elements. It has nothing to do with what are the specific elements. Okay, similarly, generators, right? We are only interested in which elements, when operated on itself again and again, will give you the entire group. Okay, so now what we'll do is we'll use Zn, okay, as a prototype of all cyclic groups, all finite cyclic groups. Let me be more specific. Okay, of a finite cyclic group. Once we sort of analyze Zn completely, right? By analyze, I mean I figure out, given any n, what would be the generators and what would be all subgroups of this. Then I can use the same results in order to analyze generators and subgroups of any of the other cyclic finite subgroups that I've given here, or I mean, I've not even mentioned them here, maybe it doesn't really matter, right? Is that clear?
Yes, sir.
Okay, so then comes the main result here. So let H be any subgroup of Zn. Okay, then first important result that we are going to show is that as far as H is a subgroup of Zn, it has to be cyclic. Okay, you cannot have a non-cyclic subgroup of this cyclic group Zn. Right? Is the statement clear? And once again, it may sound absurd to state otherwise, right? May sound very absurd to say that a subgroup of a cyclic group may not necessarily be cyclic. Again, the idea is, can we prove that? Okay, so let's try to prove this. Right? How do we prove this? So of course, we are going to pick an arbitrary subgroup of Zn. Okay. One can have, of course, H equals 0, right? Only the 0 element. the identity element. This is a subgroup as well, right? The trivial subgroup. Then, is this a cyclic subgroup?
Yes, sir.
And how do we show that? The generator is just 0. Okay, so we are done. So then let's look at this case where H does not contain only the 0 element. Okay? Then let D, right, be the smallest positive integer in H. Okay, and this is guaranteed simply because we have said that H does not contain only the 0 element, right? So it has to have some positive element, can have several positive elements, out of which I am going to choose the smallest positive element. Right? I hope so far you're following me.
Yes, sir.
So if D is the smallest positive integer in N, what can we say about the cyclic subgroup generated by D?
Sir, for any integer n, nd will be part of the group H.
H, subgroup H, right?
Because of closure property.
Exactly. So then I can directly write this is a subset of H. Fair enough?
Yes.
Now what do I need to show? I need to show the subgroup H is also a subset of D, right? If I show that, then I'm done, isn't it? So how do I show that? So let's take, I don't know, P an arbitrary element in H, okay? And I can divide P by D, right? And what will I get? I'll get a quotient, let's call it Q, dividing by D, so D, plus some remainder R, right? Yeah, right. Then what is the condition on R?
R should be 0.
No. I mean, you cannot
0 to
directly
D
say
minus
that R is 0,
R
right?
Greater than or equal to
than
0, less than D.
Less than D. How about P? P is an element in H. H is a subgroup of Zn, right? So P
should
also
be
has to be
0 to
less
N.
than N, right? 0, but strictly less than N, isn't it?
Yes, sir.
And what about QD? Also has to be less than N.
Yes, sir.
Okay. So now P belongs to H. What about QD?
Belongs to H because
It also belongs to H, right? Because of this. How about QD inverse?
Also belongs to it.
It also belongs to H. How about QD inverse addition modulo N P?
Also belongs to it.
Also belongs to H, but what is this equal to?
R.
is R. This belongs to H. Then
Implies R equals to 0 because the D is the smallest positive integer.
exactly, right? So since we have these bounds on R and D is the smallest positive integer in H, that implies R is 0, which implies P is also in the subgroup generated by D. Okay, and that implies, sorry, I am out of space here, but that implies H is a cyclic subgroup. I hope it's not very difficult to follow this proof, right?
Yes, sir.
Okay, so this is one. Next, the order of H, it's a whatever this subgroup you pick will always divide N. So in some sense you can see, I mean, if you have attended the tutorial and if you are following my explanation of question 8, this is sort of a special case of Lagrange theorem. Okay, Lagrange theorem applies to any subgroup of any group. Here we have picked up a cyclic group Zn and its subgroup, which we have already shown will be cyclic. The order of or the number of elements in this subgroup H will be a divisor of N. How do we show that? So we have already shown, remember, H is equal to D, where, sorry, the subgroup generated by D, where D is the smallest positive integer in H. Right? What is the order of the group?
It's N.
N. Right? Okay. Now, what happens if I divide N by D? Again, I'm sort of using the same proof strategy. N would be
But some quotient and remainder.
some quotient and remainder. Good. Okay, and the condition on remainder, as usual, is that it has to be between 0 and D minus 1. Okay, then I think you can now follow the same proof process of the last result. Right. What do we know about D? D is in Zn, right?
Yes, sir.
So, and D is in H as well. What can we say about N and QD?
Both are in Zn.
And
R is also in Zn.
okay.
Then R is equal to 0.
Can you sort of write it properly? The D is in H, right? So QD is in H. What would QD inverse be? It would also be in H.
n plus qd in inverse is in h,
Right.
so r is in h, and then r is the smallest integer, so this will be 0 only.
Do you see that, everyone? So it's the same proof basically, since R is in H and R is bounded above by D, so that implies R is 0. What does that mean?
That's means n divides, matlab order of h divides by n,
Order of D,
divides by.
right, divides N. And remember, order of D is the same as order of the subgroup generated by D. So therefore, this also divides N. Okay. Okay,
Sir,
let's go.
this order of subgroup divides order of group is true for non-cyclic groups
Yes,
as well. But here
yes,
we have proved only for cyclic group, right?
yes. The general result is what is called the Lagrange's theorem, right? We have not seen it yet, but it's basically a version of that, as I hope you can realize by now.
Yes.
Okay. Then let's come to the final result of this class as well. Ooh, I'm sort of approaching the time limit. This is what basically we want, right? Generators, right? How do we know what are the generators of a given cyclic group or a cyclic subgroup? Okay, so says that if I pick an element A in H, right, then the order of that element A is nothing but the order of the GCD of A and N. Oh, sorry. So that was this statement. This statement says that the subgroup generated by A will be the same as the subgroup generated by the GCD of A and N. Okay, and because of this, the order of the element A is the same as N divided by the GCD of A and N. So let's hold the proof for a moment. What does this imply? If I give you a cyclic group and I ask you to find out the generators, how will you find out? So for example, if I take Z12 and I ask you to find out the generators of Z12.
We will find the numbers between 0 to 12 which are co-prime with 12.
Exactly, right? Because you can clearly see co-prime means GCD has to be 1. If GCD is 1, the order of the subgroup generated by that element will be equal to N, which is basically the entire group. So what are the generators of Z12?
1, 5, 7, 11.
1, 5, 7, and 11. Which is why I hope you see that in this example of the group generated by rotation by 30 degree, that's basically like Z12. The generators were R30. 5 is basically the same as R150. And 7 is the same as R210. 11 is the same as R330. Make sense?
Yes, sir.
Okay. How do we prove this now? So Again, the same strategy. Let D be the smallest positive integer in A. Right? Then what is the relation between this subgroup and this subgroup? You already done this, right?
Both will be equal.
I mean, again, I'm hearing only one voice. I hope this is clear. We just proved this slide ago. Where is it? Over here, right? So we took any subgroup of this Zn, let's call it H, and we picked up, assuming H is not only 0, we picked up the smallest positive integer denoted by D over here. And then we basically proved that H is equal to the subgroup generated by D. So that's exactly what we are using over here. Yes?
Yes, sir.
Okay. So then, since A is also in D, right? What does it mean? Means D will divide what? A, and D will divide N, both, right?
Yes, sir.
See, all I'm trying to do is to show that this D has to be the GCD of A and N, right? I hope that is apparent from this statement itself. In order to show that it is GCD, I have to show two things, right? One is that it divides both A and N, and secondly, it is the greatest such divisor, common divisor. Okay, since A is in D, the subgroup generated by D, obviously D divides A. Why should D divide N?
Lagrange's theorem.
So don't use Lagrange's theorem for now. It comes from this, right? Order of the subgroup will divide the order of the group N. Okay, so D is nothing but the right, the order, right? So D would divide N. Okay. Are you with me?
Yes, sir.
Yes, sir.
Okay. What else? So A, the subgroup generated by A and subgroup generated by D are the same. So therefore, D also belongs to this. Okay. So D would also be a multiple of A, isn't it? In what sense?
Sir, A divides D.
No. So that is fine. So okay, well, you're saying A divides D. So in what sense? See, D is the smallest element in the subgroup generated by A. So it's sort of counterintuitive when you say that A divides D, isn't it?
Sir, but this set is having only the powers of A.
Yes.
So if D is one of that any element, then A will divide D.
Exactly, but just remember this is because of the modulo n operation. Right? To think of it this way, we are saying D is the smallest integer. Then if it is the smallest integer, there can be no divisors of that, right? But we are saying A divides D
A
in the
divides
sense.
D plus N, sir.
Exactly. So D. So what is D? I can write D as some k times a modulo n, right?
Yes, sir.
Yes, sir.
So then T can be written as Ka plus, remember I need to show that D is the GCD of A and N, right? So I have to be able to write D as a combination of A and N. That is apparent because now I can write D as Ka plus some Q
Plus some
times N,
Q times N. Yes.
right? Where K and Q are some integers. What is left now? I need to show that D, so I've already shown D is a divisor of both A and N, right? I need to show that it's the greatest divisor. So I choose some, I should use a different color here. Let, I don't know what is the symbol that I have not used, maybe P. Okay. So let us say P is another divisor of A and N. What do I need to show then?
P divides D.
Exactly. Can you do that?
Yes, sir.
How?
Placing A equals to P times somewhat T1 and
Okay.
N
Okay.
equals to P times T2. Placing it in the
Then,
above equation.
so D will be K times PT1 plus Q times NT2.
PT2, sir.
Oh, sorry. Oh, yes, it is just KT1 plus QT2 times P. So therefore, P divides T. That implies T is the GCD. We are done. Okay. This is where we'll stop. Right, so we have shown that any subgroup generated by A is the same as the subgroup generated by the GCD of A and N. This is true for Zn, but Zn we said is just a prototype example for any cyclic group of order n. Okay, so it doesn't really matter what is the cyclic subgroup you are sort of working with. Right? All you have to do is to use those elements, replace the elements of Zn by appropriate elements and conclude the same. Okay, so yeah, thank you and see you guys again on Friday.
Sir,
Yes,
sir, if we generate a group by all elements of Zn, like we generated in Z6, then
right?
elements of 2 and 4 are equal, and
Yes,
there that are means 3 3 times Z2, and elements of 3 means group generated by 3 is 3 times Z2, and group generated by 2 is 2 times Z3.
okay.
So it is also general.
General in the sense, so they have this GCD relation, right? So if you take A as 2, right? So 2 and 6, right? The GCD is 2. So 6 divided by 2 will be 3. GCD of 3 and 6 is 3. So 6 divided by 3 will be 2.
Yes, sir. So the group generated by elements are GCD of A comma n times
Right.
Z n by A.
So that's the same thing, right? I mean that is
Yes,
what we proved. The third point implies that, isn't it?
Yes, sir. Got it.
Okay.
Okay, sir. Thank you.
Sir,
Once again, yes, go ahead.
if possible, can you share the recording of the lectures? Because sometimes in lecture, due to connection and sometimes due to speed, we can't understand. So for next lecture, we can do understand so that our previous
Right. So,
lectures are
right. Yes. So as I said, once the scribes submit their notes, I will share the recording as well as these slides both.
But sir, sometimes 2-3 lectures come immediately, so previous lectures are not clear. So new lectures
Okay.
are not able to catch. We are not able to catch up.
Okay, fine. Then okay, I'll maybe upload the slides and the recordings at maybe by the next day of the lecture. Okay.
Yes, sir. Thank you, please.
Okay. No problem.
Thank you, sir.